Somewhere over the Pacific in 1944, a Navy fighter pilot feels his aircraft shudder as a Japanese cannon shell tears through the front of his engine. He is 100 miles from his carrier, over open ocean, with nothing beneath him but several thousand feet of air, and then several thousand fathoms of water. The shell has done real damage. It has punched clean through one of the cylinders of his big air-cooled radial engine, blown the top off it, left the engine running on the cylinders it has left. The aircraft vibrates, oil streaks back across the cowling, but the engine keeps running. Down one cylinder, hammered, wounded, it keeps turning the propeller, and it carries the pilot the 100 miles back to his carrier, and sets him down on the deck, alive. Mechanics count the damage later and shake their heads that the thing flew at all. Now imagine the same shell, the same hit, on a different kind of engine. Imagine that instead of an air-cooled radial, this pilot had been flying behind one of the sleek, powerful, liquid-cooled inline engines that drove the fastest fighters of the war. The kind of engine in the P-51 Mustang and the Spitfire, the engine that so many people considered simply better. That engine is cooled by liquid, by a glycol coolant pumped through passages around the cylinders and out to a radiator, and that coolant is held in by thin metal and by miles of plumbing. The same cannon shell that merely wounded the radial would have opened that cooling system like a knife through a water balloon. The coolant would have sprayed out into the slipstream in seconds, and with its coolant gone, the liquid-cooled engine would have overheated and seized solid within a minute or two, and the pilot, 100 miles out over the open Pacific, would have gone into the water and died. This is the decision at the heart of our story. In 1944, at the very peak of the piston engine's development, the United States Navy was offered the most powerful, most glamorous, highest-performing type of aircraft engine in the world, and it said no. It rejected it, deliberately and finally. And the reason it rejected it is one of the most quietly brilliant engineering decisions of the entire war. To understand what the Navy turned down, you have to understand why the liquid-cooled inline engine was so admired, because it genuinely was the engine of the war's most celebrated fighters. When people picture the great fighter aircraft of the Second World War, the ones that live in memory, they very often picture aircraft powered by liquid-cooled inline engines. The North American P-51 Mustang, with its Packard-built Rolls-Royce Merlin, the fighter that escorted the bombers to Berlin. The Supermarine Spitfire, with its Merlin, the savior of Britain. The Lockheed P-38 Lightning and the Curtiss P-40 with their Allison V-12s. The German Messerschmitt Bf-109 with its Daimler-Benz. These were, by many measures, the highest-performing fighters of the war, and they were all powered by liquid-cooled inline engines. The reason these engines delivered such high performance comes down to their shape and their cooling. A liquid-cooled inline engine arranges its cylinders in a line or in two lines, forming a narrow V, cooled by liquid circulating around them. Because the cylinders do not need to be exposed to the airflow for cooling, the engine can be built long, slim, and narrow, presenting a very small frontal area to the air. And frontal area is drag, and drag is the enemy of speed. A slim, liquid-cooled engine let an aircraft designer build a sleek, low-drag nose, a knife-shaped fuselage that slipped through the air. The air-cooled radial engine, by contrast, arranged its cylinders in a circle so they could all catch the cooling wind, which made it wide and blunt, a broad disk of an engine that presented a large frontal area and more drag. For raw speed and high-altitude performance in a land-based fighter, the liquid-cooled engine's slim shape was a genuine advantage, and it was why the fastest, most glamorous fighters used it. This was the engine that won the glory, and it was exactly the engine the Navy refused to use. Here is the paradox. The United States Navy, which fought the largest naval air war in history and utterly dominated the skies over the Pacific, did so while deliberately refusing to use the type of engine that powered the war's highest-performing fighters. Every Navy carrier fighter, the Grumman F-4F Wildcat, the Grumman F-6F Hellcat, the chance-fought F-4U Corsair, was powered by an air-cooled radial engine, the blunt, draggy, less glamorous type, while the Army's most celebrated fighters and the enemy's best used the slim, fast, liquid-cooled inline. The Navy looked at the engine that everyone admired, the engine of the Mustang and the Spitfire, and it turned it down, not once but repeatedly, culminating in a final and deliberate rejection in 1944. The resolution of this paradox is the whole point of the story, and it is a lesson that runs against the grain of how we usually think about technology. The Navy did not reject the liquid-cooled engine because it failed to understand it, or because it was hidebound and conservative, though many at the time and since have assumed exactly that. The Navy rejected it because the Navy understood, more clearly than almost anyone, that the best engine for a fighter is not the one that produces the most speed on a test flight over friendly land. The best engine for a Navy fighter is the one that brings the pilot home, over hundreds of miles of hostile ocean, after taking battle damage, from a carrier deck that pitches and rolls in the swell, maintained by mechanics working in a steel hangar in the middle of the sea. And by every one of those measures, the measures that actually mattered for naval warfare, the air-cooled radial was not the inferior engine the Navy grudgingly settled for. It was the superior engine the Navy wisely chose. The rejection of the most powerful engine was not a failure of vision, it was vision itself. The popular history of wartime aviation is written largely around the glamorous fighters and their liquid-cooled engines, the Mustang and the Spitfire and their like, and it tends to treat the air-cooled radial as the lesser engine, the one used where the good engine could not be had. It misses that the Navy's commitment to the radial was not a limitation imposed on it, but a deliberate strategic choice, made early, defended consistently, and vindicated overwhelmingly by results. It misses that the Navy actually flirted with the liquid-cooled engine, invested real money in it, ordered an actual fighter built around one, and then, after careful evaluation, deliberately walked away. And it misses the specific, decisive reasoning behind that choice, the hard engineering and operational logic that made the blunt radial the right engine for war over water. This story is about that reasoning, and it is a richer and more surprising story than the simple one where the Navy just happened to use radials. It is about a decision that stretched from 1921 to 1944, a quarter-century of the Navy holding to a conviction that the rest of the aviation world doubted. It is about the one time the Navy nearly changed its mind, the strange and powerful engine it almost adopted, and the final reckoning in 1944 when it evaluated the liquid-cooled path one last time and shut the door. And it is about why that decision, which looks on its face like the rejection of the better engine, was in fact one of the wisest engineering judgments of the war, a judgment that helped the Navy win the greatest carrier war in history. To understand it, we have to go back to where the Navy's conviction began, more than 20 years before the decision of 1944. The Navy's rejection of the liquid-cooled engine in 1944 was not a sudden decision. It was the final confirmation of a bet the Navy had placed a full generation earlier, in the years right after the First World War, and understanding that original bet is essential. In the First World War, the best aircraft engines had been liquid-cooled. The finest Allied aircraft of that war had flown behind water-cooled engines like the Hispano-Suiza, and the entire aircraft engine industry, coming out of the war, was deeply invested in the liquid-cooled path, primarily large V-type engines. The liquid-cooled engine was the established, respectable, low-risk choice, and the air-cooled engine was regarded as crude and troublesome, unable to cool its cylinders reliably. But a few far-sighted people saw something else. In 1920, the National Advisory Committee for Aeronautics, the government's aviation research body, noted that air-cooled radial engines could offer ship-based aircraft a better power-to-weight ratio and, crucially, greater reliability. And the Navy, thinking hard about the peculiar demands of flying from ships over water, found that argument compelling. In 1921, the United States Navy made a remarkable and forward-looking decision. It announced that it would order only aircraft fitted with air-cooled radial engines, not primarily air-cooled, only air-cooled. It was a stunning commitment to a technology that was, at that moment, still unproven and widely doubted, and it reflected the Navy's clear-eyed understanding that its needs were fundamentally different from those of a land-based Air Force. The Navy had placed its bet, in 1921, on the air-cooled radial, and it now needed someone to make that bet pay off, to build an air-cooled engine reliable enough to justify the Navy's faith. That someone was an engineer we have met before in these stories, a stubborn outsider named Charles Lawrence. Charles Lawrence was the man who, more than anyone, made the air-cooled radial a practical reality, and he did it with Navy money and Navy faith behind him. When the Navy committed to air cooling in 1921, the air-cooled engines that existed were not yet good enough to justify that commitment, and Lawrence, running a small engine company, was one of the few people in America who believed air cooling was the future and was willing to do the hard engineering to prove it. With Navy funding, Lawrence developed an air-cooled radial engine, the J-1, using aluminum cylinders with steel liners and the carefully designed cooling fins and valves that let an air-cooled cylinder survive the heat of combustion. The result was staggering, and it vindicated the Navy's bet completely. Lawrence's air-cooled J-1 engine ran for an unprecedented 300 hours, at a time when 50 hours of endurance was considered acceptable for a liquid-cooled engine. 300 hours against 50, 6 times the endurance. The air-cooled engine that the industry had dismissed as crude and unreliable turned out in Lawrence's hands to be dramatically more durable than the liquid-cooled engines it competed with. This was the proof the Navy needed, and it settled the matter. At the urging of the Army and the Navy, the Wright Aeronautical Corporation bought Lawrence's company, and his air-cooled designs became the Wright radial engines, the ancestors of a whole dynasty of American air-cooled radials, the Wright Whirlwinds and Cyclones and the Pratt and Whitney Wasps that would power American naval aviation for decades. The Navy's 1921 bet had paid off. It had committed to air cooling before air cooling was proven, and then it had funded the man who proved it. By the 1930s, the air-cooled radial was not the crude alternative. It was the reliable heart of American naval aviation, and the Navy had every reason to be satisfied with its choice. And then, in the late 1930s, the temptation came. By the late 1930s, aircraft engines were growing more powerful at a furious pace, and the liquid-cooled inline engine was pulling ahead in the race for raw fighter performance. The slim, low-drag shape of the liquid-cooled engine was letting land-based fighters reach speeds and altitudes that made the Navy planners wonder whether their beloved radial was falling behind. The Navy, for all its commitment to air cooling, was not blind, and it kept a close watch on liquid-cooled development. And in the late 1930s, it saw a few liquid-cooled prospects promising enough that it decided for the first time in nearly 2 decades to invest real money in the path it had rejected in 1921. The temptation took concrete form in 1941. On June 30th of that year, the Navy ordered its next generation of fighters, and alongside the air-cooled aircraft that would become the famous Hellcat and Tigercat, it ordered something unusual, a break from its own long tradition. It ordered the Curtiss XF-14C, a high-altitude naval interceptor that would be powered, in a departure from everything the Navy had held to, since 1921, by a liquid-cooled engine. And not just any liquid-cooled engine, but one of the strange and ambitious new power plants that engine makers were developing in the desperate wartime race for more power. The engine was the Lycoming XH-2470, and it was one of the most unusual engines of the war, a genuinely strange machine that pointed toward the most powerful engines then imaginable. To understand why the Navy was tempted and why the temptation ultimately failed, you have to understand what this strange engine was. The Lycoming XH-2470 was an H-block engine, And the H-block was one of the stranger answers to the central engine problem of the war, which was how to get more cylinders, and therefore more power, into a single engine. There are only so many ways to arrange a large number of cylinders. You can put them in a long line, but a line of too many cylinders becomes impossibly long, and the crankshaft too flexible. You can put them in a V, which is more compact. Or you can do stranger things, and the H-block was one of the strangest. An H-block engine is, in effect, two flat opposed engines stacked one on top of the other, each with its own crankshaft, the two crankshafts geared together to combine their power. Viewed from the end, the four banks of cylinders form a rough H shape, which gives the configuration its name. The Lycoming H-block took two flat 12-cylinder engines, stacked them, and geared them together into a single 24-cylinder engine, and this arrangement had real theoretical advantages. It packed a great many cylinders into a relatively compact space, and the two crankshaft design could be very smooth. Coupling engines like this, stacking or joining smaller engines to make a larger one, was an idea that nearly every major aircraft-building nation was experimenting with in that era. The same fundamental impulse that produced the H-blocks and the X-blocks and the coupled double engines that promised the highest power outputs of the piston age. It was the path toward the most powerful aircraft engines then conceivable, engines of enormous cylinder counts and enormous outputs. And the Navy, tempted by the performance such an engine might give its high-altitude interceptor, ordered a fighter built around one. But the H-block, for all its theoretical promise, embodied exactly the kind of complexity that would prove the Navy's undoing if it went down this path. Two crankshafts, elaborate gearing, and at the heart of it, the fundamental vulnerability of liquid cooling. And the engine, like so many of these exotic wartime power plants, ran into trouble. The Curtiss XF-14C and its liquid-cooled Lycoming H-block engine ran into exactly the kind of trouble that complex, ambitious engines so often did. The Lycoming 24-cylinder engine never really worked out, plagued by the development difficulties that afflicted so many of the exotic multi-bank engines of the war. By October of 1943, with the first prototype nearly finished, the Navy faced an awkward reality. The liquid-cooled engine it had ordered, its new fighter around was not actually available for fitting. After some wrangling, the Navy did something telling. It dropped the Lycoming liquid-cooled H-block and decided to fit, instead, an air-cooled radial, a turbo-supercharged version of the Wright R-3350, the same engine family that powered the B-29. The Navy's one serious flirtation with the liquid-cooled engine had already begun to collapse back toward the radial. And then came 1944, the year of the final reckoning. In March of 1944, the Deputy Chief of Naval Operations for Air, Admiral John McCain, sent a memorandum to the Navy's Bureau of Aeronautics requesting what would prove to be the final evaluation of liquid-cooled engine technology for naval aircraft. His language was striking. He wrote that the experiences of the war and the trend of design might point to the necessity, as he put it, of reefing our sails and departing on a new tack, of reconsidering the whole direction of naval aircraft engines in light of the relentless increase in power and weight. It was an invitation to seriously reconsider the liquid-cooled path, an honest, open-minded request to evaluate whether the Navy's quarter-century commitment to air cooling still made sense at the peak of piston engine development. The Navy was not being closed-minded. It was deliberately opening the question one last time, asking whether the most powerful engines of 1944, the liquid-cooled high-performance engines, might finally be worth adopting. And the answer it got back from the aircraft industry and from its own engineers was decisive. What happened next is one of the most revealing moments in the whole story, because when the Navy opened the door to the liquid-cooled engine in 1944, the aircraft industry itself largely declined to walk through it. In August of 1944, the Navy extended an informal invitation to its major fighter manufacturers, Boeing, Grumman, Curtiss, Ryan, and McDonnell, to propose a fighter powered by a liquid-cooled engine. The response was a quiet, collective refusal. All of them informally declined the invitation. Some of them sensed that the Navy was not truly serious about liquid-cooled engines despite the formal inquiry. Others looked at the performance requirements and concluded they were beyond reach. But the underlying message was clear. The industry that built the Navy's fighters did not believe the liquid-cooled engine was the right path for a naval aircraft, and it was not eager to try. Only one manufacturer, North American, actually submitted a proposal in October of 1944 based on a navalized version of its P-51 Mustang, the aircraft that was the very embodiment of liquid-cooled fighter performance. And another vote responded not with a design but with a study that concluded, in so many words, that other types of power plants were more suitable for future fighters. When the Navy's Bureau of Aeronautics evaluated the North American proposal in November of 1944, it concluded that the navalized Mustang failed to meet the desired performance by a wide margin. Meanwhile, the Curtiss XF-14C, the Navy's original liquid-cooled experiment, now fitted with its air-cooled radial, was tested in September of 1944 and found disappointing, its performance unremarkable, and its propeller causing an alarming shudder. By late 1944, the Navy had decided it no longer even needed the high-altitude interceptor the whole liquid-cooled experiment had been meant to produce, and it canceled the XF-14C outright. The door had been opened, seriously and honestly, and then it had been closed, firmly and finally. The Navy would fight the rest of the war and win it on air-cooled radials. Now we come to why that was exactly the right decision. The single most important reason the Navy was right to reject the liquid-cooled engine comes down to what happens when an engine is hit in combat, and it is worth understanding in concrete physical detail because it is the heart of the entire decision. A liquid-cooled engine depends absolutely and continuously on its cooling system. The engine generates enormous heat, and that heat is carried away by coolant circulating through passages cast around the cylinders, out to a radiator where the air cools it, and back again, in an endless loop driven by a pump. This entire system, the passages, the pump, the hoses, the radiator, is full of pressurized liquid coolant, and every part of it is essential. If the coolant is lost, the engine has no way to shed its heat, and within a minute or two it overheats catastrophically and seizes solid. Now consider what a bullet or a shell fragment does to this system. The cooling system presents a large vulnerable target, the radiator especially, but also the hoses and the passages spread across the engine and often beyond it. A single hit almost anywhere in the cooling system, even a small fragment, can breach it, and once breached, the pressurized coolant sprays out into the slipstream and is gone in seconds. And with the coolant gone, the engine is dead. And if the aircraft is over water, far from any friendly field, the pilot is very likely dead too. Now consider the same hit on an air-cooled radial. There is no coolant to lose because there is no liquid cooling system at all. The cylinders are cooled directly by the air rushing over their fins. A hit that would have opened a liquid-cooled engine's radiator and doomed it does, to a radial, only local damage. A shell can blow the top clean off an entire cylinder, and the air-cooled radial, deprived of that one cylinder, will keep running on the rest, vibrating, wounded, but turning the propeller and carrying the pilot home. This difference, the catastrophic vulnerability of the liquid-cooled engine to a coolant, hit versus the remarkable damage tolerance of the air-cooled radial, was, for an engine that had to fight over hundreds of miles of open ocean, the difference between an engine that killed pilots and an engine that saved them. The battle damage advantage was the most dramatic reason, but it was reinforced by a whole set of others that flowed from the peculiar nature of naval aviation, and these mattered just as much. Consider the environment a Navy fighter operated in. It flew from a carrier, a small, moving airfield in the middle of a vast ocean, and it flew over that ocean, often for hundreds of miles, with no friendly ground anywhere beneath it. In that environment, reliability was not a convenience. It was survival. An engine failure over land might mean a forced landing in a field. An engine failure over the open Pacific meant ditching in the water, far from rescue, and very possibly death. The Navy needed the most reliable engine it could get, and the air-cooled radial, with its fundamental simplicity, was more reliable. It had no radiator to fail, no coolant pump to break, no hoses to burst, no coolant to leak, none of the plumbing that a liquid-cooled engine depended on, and that gave it so many additional ways to fail. Then consider the carrier itself. A carrier landing is a controlled crash, the aircraft slamming onto a pitching steel deck and being jerked to a halt by an arresting cable. This punishment was hard on everything, and it was especially hard on the delicate brazed joints of a radiator and the connections of a cooling system, which could crack and spring leaks under the repeated shock. The air-cooled radial, having no radiator and no cooling plumbing, had nothing in that system to crack. And consider maintenance. A Navy fighter was maintained not in a comfortable land base, but in the steel hangar of a carrier by mechanics working in cramped, moving, salt-corroded conditions in the middle of the sea. The simpler the engine, the easier it was to maintain in those conditions, and the air-cooled radial, without the whole cooling system to service, was simpler. Every one of these factors, the over-water reliability, the carrier deck pounding, the shipboard maintenance, pointed the same way, toward the rugged simplicity of the air-cooled radial and away from the complex, vulnerable, plumbing-dependent, liquid-cooled engine. For the Navy's peculiar war, the radial was not just adequate, it was right. Beyond the dramatic matter of battle damage and the operational matter of the ocean and the deck, the air-cooled radial had a set of quieter engineering virtues that further justified the Navy's choice, and they are worth understanding because they show how deep the radial's suitability ran. Consider the crankshaft. An inline six-cylinder engine needs a long crankshaft supported by 7 main bearings, and a long crankshaft is heavier, more flexible, and prone to more vibration. A radial engine, with its cylinders arranged in a circle around a single point, needs only a very short crankshaft, often supported by just 2 bearings, because all the cylinders drive the same short throw. This short, stiff crankshaft produced less vibration and contributed to the radial's greater mechanical reliability, one of the fundamental reasons air-cooled radials tended to be so durable. Then consider the shape, which cut both ways but had real advantages for the Navy. Yes, the radial was blunt and draggy, which cost some speed, but because it was flat and short, front to back, it made for a shorter aircraft, which was easier to fit on a carrier, and, crucially, gave the pilot better visibility over the nose during the landing approach, a matter of life and death when landing on a pitching carrier deck. The shorter engine also gave the aircraft a smaller moment of inertia, letting it turn more tightly, a real advantage in a dogfight. And finally, consider logistics, the great hidden factor in all warfare. By standardizing on air-cooled radials, and specifically on a small number of engine families like the Pratt and Whitney Wasp series, the Navy simplified its entire supply and maintenance system. One family of engines, understood by all its mechanics, supplied by a common stream of parts, powering its fighters and its bombers and its torpedo planes alike. The commonality was itself a weapon, and adopting a liquid-cooled engine would have shattered it, introducing a whole new type of engine with its own parts and its own maintenance needs into a system built around the radial. For all these reasons, the visible and the hidden, the radial was the right choice, and the Navy knew it. The proof of the Navy's decision is in the results, and the results were overwhelming. The engine that the Navy chose instead of the liquid-cooled inline, the air-cooled radial that reached its wartime peak in the Pratt & Whitney R2800 Double Wasp, was one of the great aircraft engines of the war, and the fighters it powered dominated the Pacific Air War so completely that the argument was settled in the most conclusive way possible, by victory. The R-2800 was an 18-cylinder, two-row air-cooled radial producing around 2,000 horsepower and more, and it powered the two fighters that broke the back of Japanese air power, the Grumman F-6F Hellcat and the Chance Vought F-4U Corsair. The Hellcat, powered by the R-2800, entered service in 1943 and compiled one of the most lopsided records of any fighter in history, credited with a kill-to-loss ratio of around 19-1 against Japanese aircraft, destroying thousands of enemy planes for minimal losses and doing more than any other single fighter to win air supremacy over the Pacific. The Corsair, also powered by the R-2800, compiled a kill ratio of around 11-1 and became one of the most feared fighters of the war. These were not aircraft handicapped by an inferior engine. They were among the most successful fighters of the entire war, and they were successful in significant part because their rugged, reliable, battle-damage-tolerant air-cooled radials brought their pilots home again and again from combat over the vast Pacific in conditions that would have doomed a liquid-cooled aircraft. The Navy had rejected the most glamorous engine and chosen the most suitable one, and the skies over the Pacific were the proof. The R-2800 and the fighters it powered were the vindication of a decision the Navy had first made in 1921 and confirmed for the last time in 1944. Honesty requires acknowledging the other side of this because the liquid-cooled engine was not a bad engine, and the story is not one of a foolish choice versus a wise one, but of the right tool for different jobs. The liquid-cooled inline engine had genuine and important advantages, and for the Army's land-based air war, it was often the correct choice, exactly as the radial was for the Navy's sea-based one. The slim, low-drag shape of the liquid-cooled engine gave land-based fighters like the P-51 Mustang the speed and high-altitude performance that made them superb bomber escorts, and the Mustang's Merlin engine was one of the decisive weapons of the air war over Europe. Over land, where a coolant hit might mean a forced landing rather than death in the ocean, and where the aircraft operated from stable airfields with full maintenance facilities, the liquid-cooled engine's vulnerabilities mattered less, and its performance advantages mattered more. And even the sharp contrast between the two types of engine was partly a matter of degree. The vulnerability of liquid-cooled engines to battle damage, while real, was sometimes exaggerated, and a liquid-cooled engine with a coolant leak could often run for a number of minutes before seizing, sometimes long enough to nurse an aircraft home. The Germans demonstrated with the Focke-Wulf 190 that a well-installed air-cooled radial could make a superb land-based fighter, and the Americans and British used both types to great effect. The point is not that the radial was universally superior, or that the Navy's choice would have been right for everyone. The point is that the Navy understood its own particular war, the war over water, from carriers, against an enemy across a vast ocean, and it chose the engine that was right for that war, and it held to that choice against the temptation of the more glamorous alternative. And it was proven right. The Army made a different choice for its different war, and was also right. The wisdom was not in choosing the radial. The wisdom was in choosing the engine that fit the mission, and refusing to be seduced by an engine that was better for someone else's mission. The lesson of the Navy's decision is a lesson about the difference between the best engine and the right engine, and it is one of the most important and least understood lessons in all of engineering. It is very easy to look at a specification sheet and identify the most powerful engine, the fastest, the one with the highest numbers. It is much harder and much more valuable to identify the engine that is right for a particular purpose, taking into account not just power and speed, but reliability, damage tolerance, maintainability, logistics, and the specific brutal conditions in which the engine will actually have to work. The liquid-cooled engine won on the specification sheet, on speed and frontal area and glamour. The air-cooled radial won on the things that actually kept naval aircraft flying and naval pilots alive. And for the Navy's war, those were the things that mattered. The Navy's genius, if we can call it that, was to keep its eye fixed on the mission rather than on the specification sheet. It asked not which engine is most powerful, but which engine will bring my pilots home from over the ocean after taking fire, from a pitching carrier deck, maintained in a steel hangar at sea. And when it asked the question that way, the answer was always the air-cooled radial, and the Navy had the discipline to hold to that answer, even when the liquid-cooled engine was pulling ahead on raw performance, even when the temptation to chase the glamorous engine was strongest, even in 1944, when it opened the question one last time and could have changed course. This discipline, the refusal to be seduced by the most powerful engine when a less powerful engine was more suitable, is a rare and valuable thing, and it is the deep reason the Navy dominated the air war over the Pacific. The Navy rejected the most powerful engine of 1944 because it had understood for 23 years that the most powerful engine and the right engine are not the same thing. And in a war fought over the widest ocean on Earth, being right mattered more than being powerful. In a war fought over the widest ocean on Earth, what mattered was not the engine that flew fastest over friendly land, but the engine that came home over hostile water, and the United States Navy understood that better than anyone. In 1944, at the very peak of the piston engine's development, the Navy was offered the liquid-cooled inline engine, the sleek and powerful engine that drove the war's most glamorous fighters, the Mustang and the Spitfire, the engine that won on every specification sheet. And the Navy, having opened the question honestly one final time, said no. It rejected the most powerful engine, deliberately and finally, and chose instead the blunt, draggy, unglamorous, air-cooled radial. And it was one of the wisest engineering decisions of the entire war. The Navy chose the radial because the radial came home. It came home with a cylinder shot away, running on the ones it had left, because it had no coolant to lose and no radiator to breach. It came home from hundreds of miles over the open Pacific, because its fundamental simplicity made it reliable where reliability meant survival. It took the pounding of the carrier deck without cracking a radiator it did not have, and it was maintained in the steel hangar of a ship at sea by mechanics who did not have to nurse a cooling system through the salt and the swell. And it powered the Hellcat and the Corsair to a dominance of the Pacific sky so complete that the argument was settled forever: 19 enemy aircraft destroyed for every Hellcat lost, a verdict written in the wreckage of the Japanese air arm. In a war fought between nations, the nation that could tell the difference between the most powerful engine and the right engine, and had the discipline to choose the right one even when the powerful one beckoned, was the nation whose naval aviators came home. The liquid-cooled engine was magnificent, and for the Army's war over land, it was often the correct choice, and honesty demands we say so. But for the Navy's war, the war over water, the air-cooled radial was right, and the Navy had known it since 1921 and confirmed it in 1944, holding to a hard truth against the glamour of raw power. The most powerful engine of 1944 was rejected, not out of blindness, but out of vision, not because the Navy failed to understand it, but because the Navy understood, more deeply than its critics ever did, that the engine which wins the specification sheet and the engine which wins the war are not always the same engine. The Navy chose the engine that won the war, and over the widest ocean on Earth, its pilots came home. That was the decision, and it was the right one, and it was enough.